Today's notes are on relations and functions. We are going to start by talking about the definition of a relation. A relation is a pairing of input values with output values. There are four ways to represent a relation. The first would be a set of ordered pairs. So, for example, we might use the ordered pairs -3, 4, 3, -1, 4, -2, and 4, 3. If I wanted to represent them as a table of values, I would have an input, which would be my x values, and I would have an output, which would be my y values. So if I look at my list of ordered pairs, my inputs would be -3, 3, 4, and 4, and my outputs going with their corresponding parts would be 4, -1, -2, and 3. The table of values can be listed in any order. However, when we look at the mapping diagrams, we need to make sure that they are in numerical order. And instead of labeling them as input and output, they're labeled as domain and range. So my domain, or my x values in numerical order, are -3, 3, and 4, and I do not have to repeat the number, so I do not need to list 4 twice. My range in numerical order is -2, -1, 3, and 4. And to complete my mapping diagrams, you're going to draw arrows to their corresponding parts. So an input of -3 gave me an output of 4, an input of 3 gave me an output of -1, and an input of 4 gave me an output of both -2 and 3. The last way to represent a relation is a graph. And so I'm going to plot my points. So I'll have the point -3, 4, 3, -1, 4, -2, and 4, 3. We also want to note that this is not a function. And that is because the input of 4 has 2 outputs. Let's go down and look at the definition of domain and range. The definition of the domain is going to be your input values, or your x or independent variable, so for our example from above, your domain would be -3, 3, and 4. We can see this from the mapping diagram. The range is going to be the output values, which are my y or dependent variables. And again, if I look up at the mapping diagram, my range is -2, -1, 3, and 4. We've already looked at the graph number 4 being a function because the input has 2 outputs. So now let's put that into a definition. A relation is a function if each input has exactly one output. So for example 1, we are going to decide yes or no, is the relationship a function? So our answer for A should be yes, because each input has exactly one output. And I should know that because none of the inputs were repeated. If I look at example B, the input of 1 is repeated. However, it has the same output, which means that yes, this would still be a function for the same reason. Each input has exactly one output. And C, I can see that this is a function because if I look, my arrows, 1 only has one arrow coming out of it, 3 has one arrow, 6 is one arrow, and 8 is one arrow. So we can say once again that yes, it's a function, and for the same reason. The last thing on the front page is the vertical line test. It says if a vertical line passes through more than one point on the graph of relation, then it is not a function. When you're done copying down the definition, please flip it over to the next page and we will look to see whether or not the graphs on the back are functions using the vertical line test. For example 2, we are going to decide if the 4 graphs are a function. We are also going to try and identify the domain and the range. To find the domain and the range, we are going to be looking left to right on the graph. In order to find our range, which is the y values, we are going to be looking up or down. After I find the domain and range of each graph, I am going to write it as an inequality. So I'm going to start with the domain. If I look at my graph, I can see it continues on to the left because of the arrow. It also continues all the way to the right because of the arrow on the right, which means that my domain is going to consist of all real numbers. And you can either write out all real numbers or you can use the symbol for all real numbers, which is the R you see below. If I want to look at the range, I need to look at my Y values. So if I look up here, I see that the highest Y value I reach is the 4. I also see that all of the values included in my graph are those below it. I know it keeps going because the arrow shows me that this graph will continue to go down. That means that my range is going to be all Y values that are less than or equal to 4. Using the vertical line test, I can also decide that this is a function, because if I were to draw a vertical line anywhere through this graph, it would only hit the graph at one point at any time. So I could say, yes, it is a function. For example B, looking at the domain, and looking at the x values again, and looking at the graph, I see that it's all values that are between -6 and +6. You're going to write this as a compound inequality. This reads x is less than or equal to 6 and x is greater than or equal to -6. I'm going to do the same thing with the range. The lowest y value I see is -7, and the highest y value I see is -1. So I can say that my y values, there should be a y, are all the values between -7 and -1. If I were to use the vertical line test here, my line would hit my graph at 2 spots, which would mean no, this is not a function. Please pause the video and try and do examples C and D on your own. We will go over C and D tomorrow in class. Next, we're going to look at function notation. Function notation, which is written like this, is read as f of x. Functions do not have to be represented by the letter f. You're also going to see examples with g and h. You can think of f of x as another way of writing y equals. So f of x is equal to 2x plus 3, and y is equal to 2x plus 3 mean the same thing, but f of x gives you more flexibility. So how do we evaluate these functions? We're going to substitute a value in for the variable and simplify, just like we did with expressions. Remember, the parentheses in function notation do not indicate multiplication. The expression f of x means plug a value for x into the formula f. It doesn't mean multiply f and x together. So when it tells us to evaluate the function f of x equals -5x minus 7, I'm going to write that this is f of -3 so that I know that -3 is a number I'm plugging into the function, but then I'm only going to plug it in wherever I see the x in -5x minus 7. Then I'm going to simplify and evaluate. So the f of -3 stays out front, nothing happens to it, you don't multiply it together. This gives me a positive 15 minus 7, which means my answer is going to be f of -3 is equal to 8. The -3 would indicate my input, the 8 would indicate my output. Another way you'll see this is where it already gives you the number inside the place where the x was. So please try example 4 on your own. Know that you're going to have h of 6 is equal to 1/2 x cubed plus 16, and you're going to plug in 6 wherever you see an x in the equation and simplify.